So what we are saying now, that the DDC, we are talking more about the DDC now. The DDC requirement is in monitoring application. So that application is called monitoring. Okay, understanding the other communication signal information. Application of non-cooperative communication requires the following capabilities and can be architecture wise divided into the following. Okay, shown in figure 2. This one, I think, the figure 2. Yeah, this is a figure 2. So must handle simultaneous signals which are spectrally apart. Okay, the signal detection to monitoring time must be minimized in order to capture the this is one important thing that we are looking at, the signal detection to monitoring time. So when you detect, and by the time you start recording it, or you are trying to apply your demodulation algorithm on it, that should be very, very small, the time gap. Because today in military communications they use different type of communication sets, which are mainly this spread spectrum oriented, frequency hopping spread spectrum. So each hop may be as small as 1 millisecond. So the signal lies in only for 1 millisecond. So in 1 millisecond, if you take 1 millisecond only for detection and tuning, by the time you tune, signal will go to a different frequency. So that is what we are talking about. Okay, so must be realized in a smaller FPGAs to result in low power, so that man portable systems can be realized. So we are also talking about, you cannot always talk about a vehicle mounted system, or you cannot always talk about a flight mounted systems. Man portable systems are also required, and especially when you talk about homeland security, which normal police people need to carry, so they cannot be costly systems first. Okay, the section 3 explains how the proposed architecture is designed to achieve all the above requirements. Okay, the challenges in monitoring unknown signals over a wideband requires fast identification of presence of signal in the selected band and tuning the DDC dynamically. Several architectures are proposed to achieve this requirement. The digital front end common to this kind of applications is discussed in 1, and the proposed is channelizer based architecture. So very popular architecture that is seen in literature for this kind of application is channelizer. Okay, so channelizer, it's worth of actually reading more on this topic, because in this paper context that is what broadly the other variant of doing the same purpose. Okay, so channelizer is simply what a parallel filter bank. Okay, so a parallel filter bank you can achieve by implementing multiple FIR filters parallelly, or you can actually employ FFT, and FFT also you can configure it as, basically you can use it as a parallel filter bank. If you have 64-point FFT, the 64-point FFT can be considered as basically 64 parallel FIR filters. Okay, so that is what actually we mean by channelizer. Yeah, 164-point FFT core, FFT logic, that 64 FFT outputs which are coming, X of 0, X of 1, all binned outputs, their time domain variation of those frequency outputs are there. Okay, FFT as such converts time domain to frequency domain. So the frequency domain, one snapshot, you take the value X of 0 to X of 63 you get. But like that you keep doing the FFT, then on the capital X of 0 itself you will be keep getting multiple values. That you treat as a time domain signal, that becomes one filter output. Like that you have 64 filter outputs. Okay, so that has a lot of limitations. Okay, certain things we are highlighting, certain things are well discussed in literature already.
That is called as channelizer.
Yeah, that itself is called channelizer. Okay, but some post processing or pre processing, to handle this windowing effects or overlapping, all these things will be done. Okay,
and is there in that first figure?
Yeah, it's there. Okay, the filter bank based channelizer architecture divides signal into multiple small bands with FFT, and further allows decimation after complex NCO multiplication and half band filtering. Okay, so that paper actually whatever discussed I have written there. Okay, something similar to what we have done, but previous work, little simple one specific application, what they have done. Okay, the architecture proposed does not result in full frequency domain implementation. Rather, it is a mixture of both time domain and frequency domain. The channelizer based architecture is overhead for the signal monitoring application as described above. So in the paper itself it describes that is a overhead. It's going to be very high area solution and all, it's complex also. Okay, now question comes, then where channelizer is useful? I am saying signal. It is useful when you yourself know that there are so many signals coming in the whole band and you want to separate them out for simultaneous processing. Mainly in radar you see such a scenario, when so many signals are coming, okay, then you filter it, you pass that through multiple filter banks. That is what the main purpose of channelizer. Here, if you want, you can use it, okay, but that's first thing is the channelizer as such is not achieving any dynamic thing, like what the paper does. If you see, after complex NCO multiplication, it does a fixed half band filtering, okay, that is normal FFT only. We have to do something on top of that. That's what we are doing, okay. The architecture given in second reference explains the modified architecture for handling the arbitrary sample rate conversion. However, this still implements the filter in time domain and requires filter coefficient storage and high speed implementation of the MAC based on input sampling rates, okay. This architecture could be suitable at the adaptive demodulation stage level, but at the digital front end this becomes inefficient, okay. So what we are trying to claim here that this particular architecture, whatever is explained in the reference 2, that is time domain implementation, but that is designed something similar to the same purpose what we are designing, to handle the arbitrary sampling rate. We don't know in advance. By looking at the signal only, you have to find out what is the arbitrary sample. So, but the problem there is, it is a normal time domain implementation, and that is useful for one single thing only, and that is more suitable if you have, let's say I told adaptive demodulator. So one adaptive demodulator, signal is routed to it, then that is suitable, but not as a front end. Okay, that's I have written there, front end, not suitable as a front end. Sampling rate conversion with a fractional FFT is explained in reference 3. However, this is a very complex architecture to implement in FPGAs. Okay, the article given in 4 presents the basic idea of sample rate conversion in frequency domain. We have actually not discussed much about the reference 3 because proceeding in the lines whatever the reference 3 has given is more advantageous, definitely. But if you see the amount of signal processing involved in it, that's very tough, very complex. And moreover, our strength of basically proposing this architecture is, I have written that somewhere in this one, that either you take ASIC design flow or FPGA design flow, FFT being the fundamental DSP block, already highly optimized architectures are available. So you need not break your head to implement a very area optimized architecture, because in our design, the FFT being the core block, that decides ultimately our performance. Our optimization goal is very simple. But whereas if you like fractional FFT, you implement your own fractional FFT, it's enormous, complicated, and you have additional design efforts to actually optimize it. Okay. So the article given 4 actually explains the fundamentals of frequency domain filtering, but that does not talk about sample rate conversion. It's a simple only frequency domain filtering. The approach presented in the paper extends the concept and evolves a full dynamic tuning based on low area present in this paper. What we are doing, okay, multi-channel DDC. There are few FPGA IP cores used in the defense systems which are targeted for similar applications. Okay, so what we are trying to say that there are already some market available solutions like what we are doing, but that's not available as a open information. Okay, how they have done. So it makes sense to actually to research that. So some industry IP cores I have given there as a list. The work is motivated to realize such architecture in a low area implementation style. Okay, so what we are trying to aim is, even though the inner signal processing is well known, we want to evolve a architecture wise efficient scheme. Okay, rest of the paper is organized into 4 sections. The section 2 elaborates some motivating factors for frequency domain DDC. Section 3 explains the frequency domain filtering operation. Section 4 presents the proposed answer. Section 5 is for results and all. So in this section, the frequency domain. So fundamentally, what we are trying to.
Shown that you have those papers.
Yeah.
I will send a
Yeah. So what we are trying to first explain, in frequency domain, the total DDC flow in frequency domain, how it happens, we are explaining. So multiplication with the digital local oscillator. So the complex digital local oscillator shifts the signal in frequency domain. So if there is a signal something like this, you have A, its sampled version is a B. Okay, these are the sample aliases which are causing with a sampling frequency of FA. Okay, so these are images. Now this digital signal which is coming as a output of your ADC into your FPGA, now you multiply by complex NCO. That is our first part in DDC, right? So multiplying by complex NCO causes this shift, spectral shift. Okay, so as what we are trying to highlight is, yeah. So multiplication towards left is happens e power minus j 2 pi f naught n. If you multiply by e power j 2 pi f naught n, spectrum will move towards right. This is a very simple Fourier transform property. Okay, so what we are trying to highlight is, I mean, the main thing here what we are trying to say is what happens, okay, in the frequency domain at the output of complex multiplier, complex NCO and multiplier. Okay, so this is what the C is what is available. Okay, the figure 3 shows the effect of multiplying signal with a negative complex exponential. So this one. Okay, this can be achieved by simply rotating the spectrum left. Now you see, after all, this complex NCO multiplication, now anyhow signal is in frequency domain. Okay, so now you shift the spectrum after all. Okay, that's what we are trying to say. Similarly, the multiplication with the positive complex exponential signal can be achieved by right rotating the whole spectrum. I am using the word rotating, not shifting. You will get to know, it is given down. Okay, the implementation level details of proposed rotation based complex NCO is given in next section. Okay, so now here little detail we are going about that rotation itself. Okay, now the change in sampling rate can cause either aliasing or decimation or this one. No, actually here what we have done is that word why rotation not shifting we have not explained here. We have explained when we are implementing the FPGA architecture. Okay, but I remember there is a figure which is explaining that. Oh, it's not there. Why I didn't keep the figure? Actually, I think what happened here, something went off. Some lines I should have drawn on top of this. Okay, I think it's I don't know where I thought of drawing some. It's very simple. To understand that why it is rotation, why not it is shifting. First, let us understand that. See, even though the what is called the digital signal sampled spectrum is like this or this, whatever B or C, what you see with your digital signal is only the information that is between minus 1 by 2a to plus 1 by 2a, or in talking in frequency domain, minus FA by 2 to plus FA by 2. Okay, so that minus FA by 2 to plus FA by 2 only what you are seeing. Okay, so let me draw lines in the between this minus FA by 2 to plus FA by 2. So these are the lines. Okay, so minus FA by 2 to plus FA by 2. Now if you look at this, I have actually, no, I'm sorry. Yeah, this is minus FA by 2 to plus FA by 2. So what I'm trying to say is that in digital what happens is whatever you see between these two, that is only being repeated, that's all. Okay, the information is only here. Now if you see the complex NCO output after multiplying with this one, now what actually happening here is that this signal is this image. You have to see my mouse movements. Okay, this particular whatever frequency domain, it's moving towards the left. Whatever the part that is being cut from the left here is entering over here. Okay, that's what I have shown with the dotted lines here. As you can see, this dotted lines piece which has gone here, that only has come over here. So that can be achieved. So when you do FFT in your FPGA, whatever the FFT bins that you have, those FFT bins are actually from here to here, isn't it? Whatever FFT bins that you get, let's say you are doing 1024 point FFT, that 0 to 1023, whatever you see here, are nothing but actually the values over here. For the purpose of clarity, we are interpolating those points and plotting one continuous curve. But we know that the FFT output is not this continuous curve. The FFT, when you say 1K point FFT,
You have
1024 frequency domain samples only. Okay, so what we are trying to say here that out of these 1023 samples, few samples which are going out of this are nothing but you are entering over here. So nothing but if you achieve basically a rotation within 1024 samples, you will achieve the spectrum back, isn't it? Whatever is going over here, that is entering on this side. So that within among these 1024, it is trying to like a rotation. That's all. Why we are tend to call it as a, it's a shifting, because We are seeing infinite to infinite spectrum. When you are seeing infinite to infinite, you can call it as rotation. But when you are seeing between minus fs by 2 to plus fs by 2, that is the actual values that you will see in your FFT bins outputs of your FPGA core. Among them, if you see, it has to be called as a rotation only. So the change in sampling, now we are talking about how do you achieve the sampling rate conversion. That is also in frequency domain. Okay, the change in sampling rate can cause either aliasing. Okay, in imaging, general thing. To avoid this, we need to perform the filtering operation over the band of interest and then do the sampling rate conversion. Okay, so we are trying to explain the aliasing. Okay, how it happens. Okay, this we know. So filtering is usually performed with FIR filters. Okay, with efficient polyphase architecture. Okay, the input signal is convolved with the filter coefficient, convolved filter coefficients, and the sampling rate conversion is performed. Doing same in frequency domain can be achieved with multiplication of the input signal with the filter coefficients in frequency domain. Okay, so time domain multiplication of a signal. Okay, time domain convolution of two signals, one signal, other one is a filtered tabs, is equal into frequency domain multiplication of them. Okay, so the inverse Fourier transform of this product can give the time domain signal back. So after doing that frequency domain multiplication, time domain basically do this. Okay, because FFT provides a means to reduce the computational complexity of the DFT from order of n2 to order of, these are all FFT algorithms. I mean, how much multiplications are saved and all. It is often desirable to do FFT based processing in DSP systems. Okay, I mean, what we are trying to say is, if something you want to do, don't go for a DFT, compute FFT only. Okay, as FFT is most fundamental element in digital signal processing, lot of architectures were evolved to provide high speed and low area implementation. Even the computational cost of doing both FFT and IFFT in FPGA is less than conventional methods. Okay, so a lot of research are already done. People have come out with a very good architectures for FFT area implementation. All of those becomes useful to us because that only becomes our fundamental block. The DFT is a sampled version of the FFT. Okay, the DFT is a sampled version of the DTFT, which is what we are calling as Fourier transform. So multiplying DFTs correspond to circular convolution, not the linear convolution. So circular convolution can be results in time domain aliasing. So if you just go by circular convolution, then you think that is equivalent to linear convolution. Where you are doing wrong is this circular convolution and time, this linear convolution, if you see the difference, whatever the output of linear convolution, if you fold it back, I mean that end and this end, they will be added together and that will be given in your circular convolution. That is called time domain aliasing. The boundaries. Okay, like how you are seeing the frequency domain aliasing here. In circular convolution, okay, in linear, you take first do linear convolution. Let's say you take 1k points, compute and take 1k. Say 1k points, compute and do. If you do like this, then what actually you get at the output is the first 1k and second 1k, their boundary values will be summed together and will be given to you. Okay, so overall we get, no, overall you get 1k output only, but what I am saying is straightforward, you cannot use circular convolution because this time domain aliasing can be there. You have to find out a method. So that's what we had given heading as a linear convolution with circular convolution. Okay, consider a unit sample response h of n with a finite length p. Okay, so we are talking about a filter whose length is p, FIR filter, and a signal h of n L. This we already discussed, I think, right? The linear convolution as a length of this one. So to avoid the aliasing, what we do, we do time, padding of zeros for both these. One is a filter coefficients, other one is input signal. We do zero padding. Then we compute a higher point FFT. That is L plus P minus 1 point FFT. Okay, that's what I have explained here. Then we add. So that's what we are doing here. So this is what x of n. The x of n is divided into chunks of L samples each. So this L sampled one, if the filter coefficient length is P. So what we do is this, after L samples we zero pad P minus 1, then do FFT. Got it? Like that, when you keep getting for every frame you get L plus P minus 1, L plus minus 1, then these boundaries we sum up. So in the first one, whatever the L plus P minus 1 you have, in the second one whatever you have, we sum up these two, okay, and the final signal actually is stitched back after summing these boundaries. That is what we are doing. So it is to be noted that the last p minus 1 output samples will overlap the start of the next block, and the overlapping points must be added to get the proper response. This is known as the overlap add algorithm, and the figure 5 explains the same. Okay. So what is our proposed architecture? For the purpose of distilled down conversion, either we can apply rectangular window or any selected window function as a frequency domain low pass filter. So we told about how to do, but what p values you have to consider is again a question mark, because now filter has to be dynamic filter. You cannot pre-compute using your MATLAB FDA tool, and you cannot program. You have to basically dynamically synthesize something. Okay. So that's what we are talking. We can apply a rectangular window. So applying a rectangular window is a very simple option. Whichever signal is there you simply take those filter bins. Remaining all filter bins you take 0. But that has its own drawbacks in terms of rectangular window drawbacks. Or you can apply this selected window function. That is Kaiser window or any Hamming window like that. The results shall be similar to window based FIR filter design. Obviously, the rectangular window based implementation is a low area solution, as it results in only multiplying with 0 or 1. Okay. Even in other function cases, all the channels, only one memory set is used for storing the window functions. That is important. Let's say not rectangular window. Let's say you are talking about not rectangular window. I'll use a Hamming window. We will not store Hamming window multiple times. Only one Hamming window. In whichever frequency bin, wherever signal is there, we use for multiplication. Okay. So this is what our FPGA architecture. Okay. So we have this one side x of n. We zero pad with the p minus 1 samples. X of n is actually of length n samples length. We zero pad with the p minus 1. Then we compute n plus p minus 1 point FFT. Here we have two memory buffers. Okay, which ping pong is a software term used. Ping pong architecture means it's a dual buffer system. Okay. So what do you mean dual buffer system? Let's say, right. So you are going to write basically in one buffer, but whereas that next block, that is index rotate block, which is actually going to rotate, and from the bottom whatever the values are coming, they come from the second buffer. Okay. So now this index rotate block, okay, what this block is doing is, this is mapping basically by what value the rotation has to take place from the information which you are getting from the detected signal index. Okay. I should go to the top level diagram to understand this. See this one. From signal detection you are getting this information. Which are the signals where the energy is present. Okay. So actually we can also do that part, because after all you are doing FFT here. You can extract that information. But assuming that there is an algorithm, there is a method for doing it. So that fellow is giving information for us. Okay.
Where the signal?
Yes. Which are all the...
Not part of
That is not part of sampling rate conversion. So we are not talked about that. Okay. So that index, whatever the index values that gives, whatever the frequency values it gives, it could be straightforward this one, directly applying for rotate, or sometimes depending upon whether that frequency value is falling on the positive or negative side, you have to slightly just map it one to one and give it to basically this ping pong buffer rotation value. So how this scheme is achieved, it's simply achieved by one thing. Internally there is a address counter which is going to generate the address. Let's say if the n plus p minus 1 is 1024, so there is an internal address counter for this. So that the n plus p minus 1 address counter, that is 1024, it counts from 0 to 1023. That address plus whatever the value that you compute here used as the address for the block RAM. So what happens now? Instead of getting, you look at this diagram. Okay, now see, this is actually 0 address. Now here somewhere you have address 100. Now you want to achieve rotation by 100. So what is done is, normal counter which starts from 0, always you add 100 and that you is the address. So automatically what comes first is this sample comes first. Isn't it? This sample comes first, this sample comes first, and once you reach 1024, because we will use actually only 10 bit value, the counter will overflow and then the counter becomes 0. Let's say this sample, this offset is 100, whatever, 100 bins. So it means at 1024, when the true value of the counter is showing an address of 924, the summer output will become 0 at that time. So then these sample starts coming here. Got it. So it's a very simple and very efficient implementation scheme to do that. Okay. But here we made an assumption. Okay. That assumption is what? We are assuming that there is a multi-port memory is available. Means multiple read ports are available, because each signal is at a different frequency. for each intercepted signal there is separate NCO tuning is required. That's what we are talking about. So if you want to achieve that effect, you require to have multi-read port memory. Write could be only one because writing is only one. But while reading, you have different addresses. You got it? So how long? How much this assumption holds good? In ASIC, this holds good very much because in ASIC, normally this 5 read ports, 6 read ports is a very common thing. Okay, but in FPGAs, if you see, you have total only 1 and 2 read ports only you have in FPGA block RAMs. Got it? So other than block RAMs, you can also implement your own memory with multiple read ports using slice logic, but that's also going to take a lot of area. Or one possibility could be, since you know that in FPGA there are only 2 read ports for one block RAM instance. Let's say you want to support maximum 6 signals simultaneous down sampling rate conversion. Then you put 3 block RAMs. Got it? That is not efficient scheme, but in FPGA it is anyhow limitation. We have to live with that. But that is still optimized because block RAMs are not a very, it's not a very costly affair thing in FPGAs. Even the low cost FPGA would come with 1 megabit block RAM. Normal Spartan 3 also, if you see, it has a megabit of block RAM. So now this output, whatever you get, now that is shifted spectrum now. That is this spectrum. So NCO multiplication is over. Rotation itself, NCO multiplication is over. Now what is left is actually that filtering. Okay. Now what is left is a filtering. So what we are talking about filtering is here that we have actually window function. Whether it is rectangular means it is simple. Okay. In case of basically if it is hamming or hanning, then that memory, that coefficients will be stored in this ROM. Okay. Then depending upon whatever the choice that you want to make, whether it is hamming window, hanning window, one among these values are taken. Okay. Then that will be multiplied over here. Okay. So after multiplication we perform basically IFFT. Okay. Then after IFFT we do overlap and add, that we get X1 of here. We are calling it as sampling rate converted signal. Okay. So the yeah.
Sampling and the rate converted and the input and output, both of them are having memory.
No, I think I have explained somewhere. Let me see that. Okay. The if mathematical equations are unnattundi basically. Okay. The input X of n is 0 padded with p minus 1 zeros and FFT is performed this one.
And the X of n itself is padded with
X of n itself is
padded with zeros.
yeah.
After X of n, you are not padding zeros.
Oh, the input X of n is 0 padded with p minus and FFT. No. What I am trying to explain is X of n is not padded with zeros. What I mean to say is I am trying to explain the process which is done in this architecture. So the first process is X of n is padded with zeros.
Okay.
And second process is FFT performed. So that's a full sentence.
Okay.
With n minus, so I am just trying to explain the whole process here. The simplicity for filter length is considered to be n plus 1. Okay, we have considered. So it could be any value. Then FFT of 2n size will come. Okay. Then xk, this is a FFT equation. Okay, 2n size. The output of FFT is stored in dual buffer memory. This is also called ping pong buffer. As when FFT output is written in ping pong memory block, the pong memory is used to read the FFT output with the necessary shift values. Okay. So there are 2 memories. One we are calling as ping, other one is pong. That's all. The dual buffer memory system is required as the FFT output reading can start at any address value depending upon the required FFT index rotate, which depends on detected signal value. So we cannot actually, let's say, we cannot say that same time we will give on the same ROM you read also. It's not possible because for reading we require a full filled memory because it's not guaranteed that we start from 0 value. We may start from 1023 also depending upon where is detected signal. Okay. The FFT rotate can be easily achieved by changing the address offset. So we have written some equations here. So whatever the true k which is coming from the counter and that with rejected k we sum up and take a modular sum. Modular sum means what? Let's say 10 bit only output is there. So if you add 1024, if you make 1024, it will become 0. That's what I mean modular sum. The k of I is used as the read address to read the ping pong memory. Let the outputs of ith channel after necessary rotation is xi of k. Okay. After multiplying with the window function, si of xi of fk is obtained. Okay. The required decimation is achieved by selecting only 2n by d bins around the mid frequency FFT bin. These bins are streamed to the IFFT core, which is configured for computing the IFFT with 2n by d length, where d is a decimation factor which is provided by signal detection block. Now you see, actually, probably in the diagram little bit, I have written here. We are not focused, we are written here. See, what we are talking is, we are talking about a variable IFFT core that we have in our FPGA. So, what do you mean variable? Its FFT transform length is variable. Got it? So, depending upon our decimation factors, whatever decimation factors that you choose, we will configure the IFFT core with the required IFFT size. Okay? Which means, okay, let me take an example so that it becomes easy. So, n is equal to 1k. Then we also taken p is equal to also 1k plus 1. So, yeah, 2n is a FFT size and 2n is also IFFT size. Okay? So, 2n is what? 2048. So, 2048 IFFT there, whatever I have shown there, variable IFFT, it doesn't mean always I will keep actually 2048. I can do 2048, I can do 1024. Got it? I can do actually 512, 256, 128, 64, 32. I can do any one of these. That runtime I can pass it. Okay? How do I know actually for which I have to, what I have to pass? That depends upon basically from the top, whatever the detected signal index. From this we are also getting basically its bandwidth information also. Okay? Depending upon bandwidth only you will choose your decimation rate. That is what we are saying here. Okay? So very simple. If you have to understand in a very broad way, we have shifted 2k samples. First we performed FFT, we got 2k samples. We shifting is we rotated. So NCO multiplication is over. After rotation, we multiplied by the window function. Okay, whether it's rectangular window or rectangular, no multiplication at all. Putting some zeros, allowing other samples, that's all. Or Hamming window and not. After that, what we will do? Okay. Now let us say our decimation rate says 2. You have decimated the signal by 2. The bandwidth is something like that. You have decimated by 2. Means in the among total 2k samples now, we take from the mid, okay, 1k samples and drop other window and perform only 1k point FFT. Now what will come at the output now?
So only the middle 1k samples
Are taken. They are ignored because they are nothing but the FFT bins which corresponds to stop band. You got it? Now let us say you want to perform, you want to achieve what is that called decimation by 4. Then among the total 2k samples, okay, we take only from the mid 512 samples, and we compute 512 point FFT only. Remaining samples are dropped. Okay, so this 512 point FFT after coming outside, again we do overlap and add addition. So it will become again 256. So 1k is input, 256 is output. So decimation by 4. That's how it is done. Okay.
This technique is what we have transferred, or is it studying there in some
It is not directly anywhere discussed in the literature. That's what I said. I wondered initially why people have not tried this. But when I see the characteristics, let's say the input signal, the decimated signal spectrum, if I see, it's coming very much fine. Not only for single signal, even for simulated true digital signals, BPSK, QPSK also have verified. Okay. Now the challenge here is basically, we are talking about implementing a variable point FFT. So all the clock switching, there is a challenge in terms of implementation, definitely, because once you want to dynamically switch its FFT size, all its output data rates are changing. So you have to handle all that. Okay. And now here, this one, if you want to handle 6 simultaneous signals, you need to keep this kind of blocks 6 parallel, or you can have a FFT which is actually multi-channel FFT. In Xilinx course it is available. Okay. Now next what we are talking, the FFT output also results in 2n by d time domain samples. Overlap and add algorithm is performed to n by d time domain samples. So you are giving n samples, you are getting n by d time domain samples. That's what we are calling decimation by d. This limits the decimation to only 2 power I. Now here there is a drawback with this. Okay, the drawback is what? You are able to perform only decimation by 2 or decimation by 4 or decimation by 8. See, in between you are unable to decimate. Decimation by 5, 6, 7 you cannot do. That's the drawback of this approach. Got it? So because the FFT also exists in only these steps. You understood? That's why I wrote. Yeah. FFT, because FFT, IFFT is only available in powers of 2. But we told actually one remedy for it. Okay. However, the DFT course can be used for actually lower bandwidth signal. So here, that is higher D factor. Okay, which do not affect much area penalty. Okay. Now here you see what we are talking is, really when you look at 1, 2, 4 at higher bandwidth, that is acceptable. Where actually you are seeing the drawback, you see, I mean, I am seeing like this. What integer decimation which you cannot do, if you see, at lower decimation values it is not much. 1 you are able to do, 1 means no decimation. 2 you are able to do, 3 you are unable to do, 4 you are able to do, 5, 6, 7 you are unable to do, 8 you are able to do. So means only 2 or 3 are missing. But when you go to higher decimation values, this whatever you are missing, it becomes more. Got it? So what we are suggesting there, that you can use a DFT core. You can have a DFT. DFT do not have a limitation. It can be implemented for any number of FT points that can be used. So next we are talking about the results. So we have talked about actually MATLAB results. So this is a signal which is a time domain signal plus some noise. We have taken 2 signals basically. So now is it a 2 signal scenario or 1 signal image spectral image? I mean that positive and negative frequency. I think 1 signal positive and negative frequency, not 2 signals. Okay, then I should have written here or given the below figure. So this is the one actually your output. Okay, so for this what happens, this is what your filter, effectively what you are achieving is this filter. Okay, so this filter is quietly good enough. Okay, so we are also discussing here, actually when we designed that filter we have taken 80 dB stop band rejection, that filter coefficient. So this 80 dB stop band rejection you are achieving. So 0 is this level, minus 80 dB is outside that. Then next what we are explaining is that we are talking, we have done simulation on FPGA and we have done synthesis only. I have not written somewhere chip scope because we have to show those results now. So model sim Xilinx edition, what we have done, it's a spectrum. Okay, screenshot we have kept. So this is a time domain signal, this is spectrum. See, the problem with this is actually for the purpose of making the compatibility between synthesis and simulation, I have done it for only 64 point FFT. That's why you see the spectrum is not looking like a peak. Okay, we have to modify this code also and do it for 1K point FFT. If not, if we are unable to get the board by that time, so leave the synthesis part. For only simulation we have to take higher FFT codes and simulate. So I am giving all that in the future scope, something implementation and all. The presented work proposes a FPGA based complete frequency domain DDC addressing the requirements of dynamic decimation and multi-channel support. The complex digital oscillator is achieved by rotating the FFT output with appropriate value. The architecture uses one FFT core and 2 buffers to store FFT outputs, that is ping pong, and m number of IFFT cores to process m simultaneous signals. The FFT core can be chosen from Xilinx core gen with a runtime FFT length selection option. Xilinx FFT core has that runtime selection option. The work is aimed to be continued in the direction of realizing full architecture on FPGA to support multiple channels and profiling for the selected FPGA device. Okay, so the authors is a new acknowledgement.